Okay, so it's our pleasure to have Richard Bamler from Berkeley for our second speaker. I know Richard since he was a young, promising grad student. I've been following his career. Now he's established, still young geometric analyst. He has proven several nice results. The one he's going to talk about is a conjecture that has been open since I was a grad student. I actually thought that it would never been solved in my lifetime. I was proven wrong, and that's it. Yeah. And so Richard will tell us all about it. Yeah.
All right. Yeah. Thanks for having me. Thanks for letting me give a talk here. It's nice to be here. So what I want to do in this talk is I want to report on this recent resolution of the Multiplicity One Conjecture, which I did jointly with Bruce Kleiner. I'll first give a little bit of an introduction into Mean Curvature Flow, then I'll motivate the conjecture, then I'll state it, and I'll talk about a few applications, and in the end I'll give you a little bit of an insight how the proof works. Okay? And so, as always, if there are any questions, just ask. Okay? So let me start with mean curvature flow and a little bit of a background. So mean curvature flow is an equation that governs the evolution of hypersurfaces, often in Euclidean space or in an ambient Riemannian manifold. And the equation is this one here, that the time derivative of every point on the surface is equal to the mean curvature vector, which I'll call h. Okay, so the simplest possible case that you can imagine here, let's see if I can get more battery power here, is the two-dimensional case or one-dimensional case where the hypersurface is just a curve in the Euclidean plane. And then the mean curvature is just the geodesic curvature, and so the mean curvature flow would now say that this. Sorry, this is also out of battery, but would say that the wherever this kind of curve is concave, these points are going to be pushed further out, and whenever the surface is more convex, they're going to be pushed further in. Okay, and so this will cause the geometry of the surface to kind of homogenize and hopefully kind of turn this into some nicer geometry. All right, so there are three examples that we should always keep in the back of our minds. They'll show up quite often. So the first example is just the FN plane. The FN plane is just it's just flat, so the mean curvature is 0, so it'll just be constant under the flow. A more complicated example, but still very easy example, is a sphere. So I drew a one-dimensional sphere, aka a circle. So in this case, the mean curvature vector points inwards. It's just a radial vector, and this will cause the sphere to contract. But then while it contracts, the mean curvature will become even bigger. So the contraction will speed up, and the circle or sphere here will collapse to a point in finite time, whereas singularity occurs. Okay. And a slightly more complicated example would be the shrinking cylinder. This is also something that's going to show up. In this case, we take an S1 and cross it with an R, and you see that the mean curvature vector points towards the axis, and that means that the whole thing will shrink down, become singular, and collapse towards its axis. Okay, let me see. I thought I brought some batteries, but I don't know where I left them. Orange. Let's see if I can get a pointer going here. Okay. Okay, so these are very simple examples where we can really write down the evolution of a mean curvature flow. But what's of course more interesting is the case where we start with a surface that's not already optimal, that's kind of very crumpled, and we hope that the mean curvature flow will kind of improve the geometry of the surface and take it maybe to one of these models. And maybe the most basic example that one considers in this case is this famous neck pinch. Okay, so here I'm imagining a surface, maybe rotationally symmetric, that looks like these two spheres that are connected by this kind of neck-like geometry. And now you'll see that in this neck here, you have two competing effects. You have the concavity of the neck, which somehow causes the mean curvature, which would somehow want the mean curvature to point outwards, but you also have the convexity of the cross-section, which is a circle in this case, which will want the mean curvature to point inwards, okay? And so depending on which one's bigger, we'll decide whether this neck is going to shrink or expand under the flow. So let's suppose that the mean that the kind of curvature of the cross-section dominates. Well, in this case, then the neck will contract. But then now the neck is even thinner, so the cross-sectional curvature will still dominate, or will become even bigger. And so this will cause the neck to contract more and more up until some point where the neck develops the singularity. Okay? And so the important thing here is that the singularity really only occurs in this region. Here, the flow just survives up to the singular time and remains smooth. And it somehow seems like the flow hasn't done its job on these two parts. So we would like to continue the flow past that singular time. And well, how can we do this? Well, the standard way of doing this would be to remove that point in the middle. And this will cause a slight topological change, but it also gives the flow a chance to kind of resolve the singularity, and then we can evolve the flow past the singularity, okay? So we'll become rounder and rounder, and then at some point, we're going to have these two spheres which just vanish in a point. Okay? So we see these two different kind of singularities, cylindrical ones and spherical ones. And so this is somehow the expectation that has driven research in mean curvature flow over the last few decades. So this expectation is that starting from any embedded hypersurface, there should be some kind of singular mean curvature flow that kind of forms and resolves singularities. I'm saying this is a mean curvature flow that flows through singularities. And in some sense, the singular set, so where kind of the topological change happens, should be in some sense small. It should have low dimension. And typically, and I'll make this more concrete during the talk, the types of singularities that we see should either be spherical or cylindrical. Okay? And then you can ask questions whether this flow is actually uniquely determined by its initial condition. For example, is there more than one way of resolving such a singularity? And this is something I'll touch upon as well. Any questions? All right. So maybe the first time that this expectation has been made concrete was in research of Brian White about 20 years ago, who considered the case where we have a mean convex initial data. So we look at initial data where the mean curvature vector always points inwards. That's a condition that's preserved under the flow. And he could show that this expectation from the previous slide is exactly met. So he could show that in that case, there is a unique mean curvature flow through singularities, and the flow only incurs spherical or cylindrical singularities. The singular set has parabolic dimension at most n-1. So if you sit down, this is exactly the dimension that you would expect. And especially in dimension 2, this is the case that I'm mostly interested in. That means that M is smooth for almost every time t.
What's the meaning of parabolic dimension?
So you're gonna count the dimension within space-time, and you're gonna assign 2 points to the time direction.
2 dimensions.
2 dimensions, yeah. So yeah. Mm-hmm. Any questions? All right. So what I want to do now is I want to remove this condition of mean convexity. I want to look at a general initial condition, and I want to understand what happens when the flow becomes singular and how can we flow through such singularities. Okay? And to do this, I want to just make sure that we're all on the same page and that we have like this same terminology. So let me just use 2 slides to be a bit more precise how we can actually characterize singularities through what is called a blow-up analysis. So how do we characterize singularities in geometric flows? Well, we use parabolic rescaling. So the idea is that the mean curvature flow equation is invariant under rescaling of distances by some factor lambda and time by some factor lambda squared. Okay, so you can think of distances as being measured in meters and times as being measured in square meters. Okay? So this preserves the mean curvature flow equation, and this allows us to kind of zoom into the flow near singular points. And so now the important thing that I want to make clear on the slide is that we don't only want to zoom into the flow by looking at time slices, but we want to kind of consider the entire flow and kind of zoom into the entire flow. So imagine, and so maybe to explain this, imagine that you have this setting from before. This is the flow that becomes singular in this kind of cylindrical singularity, and we would like to analyze the singularity. And so now I really want to look at the entire flow. So let me normalize things in such a way, for simplicity, that the singularity occurs at time 0. So this is the time -1 slice. And I'm going to imagine that the singularity occurs at time 0 and at the origin. Okay? So I'm going to now imagine the entire flow. I cannot draw the entire flow, so I'm only going to draw the time -1 time slice. But I'm thinking of this as being the entire flow. So now let me take this entire flow and let me rescale it by a factor of 2. Then I get a flow that's defined from time -4 to time 0. The resulting flow still has a singularity at the origin and at time 0. And this is the time -1 slice of that flow. Okay? But it's the entire flow that I've rescaled. Of course, the time -1 time slice of this flow is the time -1/4 time slice of the original flow rescaled by a factor of 2. Okay? And then I can repeat this. So I can see these flows that are defined on larger and larger backwards time slices. And they kind of correspond to these parabolic rescalings. And each of these flows becomes singular at the origin and at time 0. Okay? And so when I do this, I zoom into these flows. And I hope you agree with me that these flows become more and more cylindrical. So they look more and more just like the flow where I take the round cylinder and let it degenerate at time 0. Collapse to an axis. Okay? So I'm going to take a limit, and in the limit I'll get a cylinder which again becomes singular at time 0 and along an axis that passes through the origin. Okay. Does this make sense? Okay. So now let me, okay.
Why do we scale time by square?
This is just because the mean curvature flow equation is a parabolic equation, so you have like a time derivative is a Laplacian. So that's how
this doesn't depend on dimension.
It doesn't depend on
Curvature is two-dimensional.
Yeah. Okay, so let me now focus on the case where n is equal to 2. So let me focus on surfaces in R3. Many of the things that I'll say, they're also true for higher dimensions, but this is where our result is true. So now, what I told you on the previous slide has been made precise by some seminal work of Ilmanen in '95. So what he could show is that if we have some mean curvature flow that develops some singularity somewhere at a point, then we can look at these parabolic rescalings for lambda I going to infinity, and we can pass to a subsequence, and then these parabolic rescalings, they will converge to some limit, which is then defined from time -infinity to time 0. And this limit is what we call the singularity model, or the tangent flow. It's like a tangent space. When you kind of take a manifold and you rescale it more and more, then you're going to converge to the tangent space. So this is kind of how you should think about it. Okay? So this result essentially tells us that if we want to understand the singularity formation, then this result can reduce this study to the classification of possible singularity models. These guys M infinity. But there's a catch, and I'll get to this in a moment, which is that we may see within this limiting process, we may see this kind of potentially see collapsing of several sheets to some limit which then has higher multiplicity. And I'll get to this in a moment. And that's why we only assume weak convergence. But
So what is the meaning then of weak convergence?
It's a measure theoretic. You'll see in a moment that I don't need to define this, but it's like some measure theoretic convergence.
Like varifolds or something.
Some varifolds, you can just, or weak convergence of the measure,
So in this theory, is the convergence unique? Or the limiting measure is unique?
That's a good question. I don't think that's known in every case. That's always unique. So, in the cylindrical case, it's unique. But in certain conical cases, it's also. I'm not sure it's unique. But, okay. So what do we now do with the singularity model? Now we've extracted the singularity model. Now we need to study the singularity model. What can we say about the singularity model? And to do this, we can use an idea of Hiskin, which is used very often in this field, which is a monotonicity formula. So what did Hiskin do? Well, he considered this quantity here, which we call the ambient Gaussian. So you just imagine that you have Euclidean space, the ambient Euclidean space, and you imagine that you have a Gaussian that's centered at your singular point and which flows backwards in time. And the only thing that somehow looks a little off here is that the Gaussian pretends that it's in one dimension lower. So if you're in three-dimensional Euclidean space, it's kind of is the Gaussian that would actually be true for the two-dimensional Euclidean space. Okay? So imagine this as some kind of Gaussian flowing backwards out of the singularity, but in the ambient space. And then you can take this Gaussian and you can integrate it over time slices before you get to the singularity. Okay, so if you go tau far away from the singularity, so here I assume the singularity is at time 0, then you just integrate this Gaussian over the time minus tau time slice. Okay, and so this is a scaling invariant quantity, and Huisken showed that this is monotone in tau. Okay? And this is a quantity that's scaling invariant and it passes through the limit. So if you get this limit here from parabolic rescalings of the original flow, where this Gaussian area was monotone, then in the limit the Gaussian area has to be constant. Okay? So the Gaussian area of this guy has to be constant, and therefore you have to have the equality case in the monotonicity formula. And this gives you very good information. This tells you that this formula is true, so that the mean curvature, it means that the mean curvature vector is proportional to the normal part of the position vector. And that immediately implies just that the entire flow evolves via modular rescaling. So this singularity model is really just given by a single surface satisfying an equation like this, which is something almost like a minimal surface equation, and the entire flow just rescales the surface. Okay? So there are two examples of this type that we've already seen. These are the spheres and the cylinder. Okay? If you take a sphere, that would be a potential singularity model. And in a sphere, the mean curvature vector is proportional to the position vector. And a sphere also evolves by rescaling. So we call it a shrinker. It shrinks down to a point, and that's a singularity model. And the same is true for a cylinder. Well, the normal part of the position vector is proportional to the mean curvature, and the cylinder also evolves modular rescaling.
Why does your row in the integrand practical there have a subscript?
The row here?
Yes.
So you're integrating the Gaussian over the surface.
Yeah. Easy asking
So that's where it's centered? Is the 0, 0?
Yeah.
Oh, so it's centered at 0. Sorry, I forgot to add this in here.
Okay.
It's a center where I
Yeah.
imagine the
Yeah.
singularity to be.
That's
Yeah.
what you want to simulate.
Yeah, sorry. I think I simplified the slides at some point.
But this would still be monotone even if you centered it somewhere else.
It would still be monotone, but
But
then
it would tell you not very much.
it would not tell you very much, because then if tau is very small, it will just go to 0. Yeah, good point. So any other questions on this? So this is a little more technical, this slide. But let me just summarize this one more time. So we want to study the formation of a singularity of a single mean curvature flow. And this theorem tells us that to do this, we just have to understand singularity models. And now this discussion tells us that singularity models are just given by shrinkers. So that means that in order to understand singularity models, we just have to classify all possible shrinkers. Okay, so things that satisfy this equation. And how hard can this be? Well, it turns out very hard, because there are a lot of different, very complicated shrinkers. There's a whole zoo of them. So they're not only these cylinders and spheres, but they're shrinkers with very high genus and very complicated asymptotic behavior. So here's just one example due to Capeliers, Klein, and Müller, which looks roughly like this. So the way you can imagine this shrinker is as follows. Take the union of a plane with a sphere. So of course that's not a surface because they intersect in a circle. But then you can somehow remove that singularity where they intersect by drilling genus along that intersection circle. So it looks kind of like this. You have these kind of holes that go backwards and forwards. Okay, it's a bit hard to imagine. And then you can take that surface and you can kind of slightly perturb it in space, and then that surface will satisfy the shrinker equation. Okay? And when you do this, then that Euclidean plane actually becomes some kind of corrugated cone. So it's like a cone over some kind of sine curve. And that sphere, of course, doesn't really look like a sphere anymore. Okay? So just to make it clear that, make this clear one more time, if I take this surface and if I evolve it under mean curvature flow, then that surface will just shrink modulo rescaling, shrink by rescaling, and will converge to this corrugated cone. So that knob will just kind of disappear in the vertex of the cone. Okay, and this would be a singularity, and that's the singularity model for that singularity. So you could see these very complicated singularity models. So this is in some sense bad news that you could see this difficult singularity models, but the good news is that the good singularity models, so the spheres and the cylinders, they're still in some sense distinguished in the distinguished, like the kind of the more typical singularity models if you just impose some further assumptions. So for example, if you want your shrinker to be mean convex, which was done in White's work, then the only mean convex shrinkers are only cylinders or spheres. Okay? Or if you impose that your shrinker is stable, so that's some kind of linear condition associated with genericity, then again, the only stable ones are cylinders and spheres. And the same if you impose genus 0, this is a result due to Brendle, the only genus 0 shrinkers are cylinders or spheres. Okay? So in other words, anything that is not a cylinder or a sphere will violate all these three conditions. That's why the kind of cylinders or spheres are so typical. And I'll get back to this in a few slides. Any questions on this? Okay. So now let me get back to the actual Multiplicity One Conjecture, and just to kind of remind you one more time what we were dealing with. We wanted to consider, that was, that's what I wrote on the previous slide. We considered a mean curvature flow that becomes singular at some point, x naught, t naught, let's say. And in order to understand the singularity formation, we shifted the flow so that the base point corresponded to the origin and at time 0. The singular point corresponded to the origin and at time 0. And then we looked at parabolic rescalings. And this result of Ilmanen said that the limit has to be a shrinker, but the limit could occur with higher multiplicity. So in theory, you could see several sheets collapsing, and in the limit, you have something of higher multiplicity. Okay? And then in the same paper, he conjectured that actually this higher multiplicity is not going to happen. Okay? And therefore, so that's a very basic conclusion. Then this will imply that the convergence is even smooth. So that's why I didn't define what weak convergence is here. Okay. So this collapsing of several sheets is not going to happen. All right. And so this is what we resolved. So we resolved that the Multiplicity One Conjecture is true. Therefore, the convergence is smooth. And in addition, we showed that if we look at any blow-up limit, not just tangent flows, then the limit again has multiplicity 1. So a tangent flow is a limit where we blow up the flow, but we keep the same base point. It's always the same base point. But even if we allow the base point to change, and all we require is that the scaling factor goes to infinity, then these limits are again only multiplicity 1. So in that case, even in that case, you don't see collapsing of several sheets.
Can I just check your theorem, your hypothesis here? You don't assume mean convex or generic or anything.
No, nothing. No. Yeah.
So these singularities could be these higher genus things, but they only still occur.
Yeah, they only occur. Yeah, correct. Yeah. Mm-hmm. So we only assume this is dimension 2 surfaces in R3. We don't assume anything else. We can even consider flows that have already flown through certain singularities. And then the next singularity that shows up is also only as multiplicity 1. And so to the last point, this implies that a minimal surface can never show up as a rescaling, as a blow-up limit. Okay, so this is something that was somehow people were afraid of for a long time. And this follows from the last point, so if you can think about this. And then, as a byproduct of the theory, let me just mention this briefly, is that we found a pretty elementary notion of what it means for a mean curvature flow to flow through singularities. We call this almost regular mean curvature flow. And this kind of notion covers all the interesting cases that people have been considering in the past. Okay? So maybe I should say to this is that people have been trying to kind of make sense of what it means for a mean curvature flow to flow through singularities or to have these kind of singular points. And the strategy was always to kind of make sense of the mean curvature flow equation on the singular set. Okay? And so this was done either through some kind of a weak formulation of the mean curvature flow, meaning a Berkeley flow, or a viscosity principle where you kind of made sense of the evolution equation through a viscosity principle. But in this definition, we basically discard all these ideas and we're only looking at the mean curvature flow, or we're only looking at the regular set, where we can just write down the equation explicitly, and then we just say the singular set is small enough in the way that it turns out to be anyway, and that's good enough to write down the theory. So it's much simpler than what has been done before. And we have an existence theory within this class, starting from every closed embedded surface. Okay. Any questions?
So the reason why you say minimal surface cannot occur is because whatever blow up you do, you know it can't be asymptotic to 2 planes at infinity or 3 planes, because then if you got that, then you adjust the scale so that in the limit you'd get 3 planes or 2 planes. Yeah. That's impossible.
Yeah, then you get high.
So the general statement is you can never get a surface which is asymptotic to more than 1 plane.
Yeah, correct. Yeah. Any questions so far?
Okay. So I'm glad I solved the question.
All right, so let me now talk a bit about the applications. And to preface this, I should say that there's been a lot of excellent research on mean curvature flows, especially in the last decade. And people have obtained a lot of very interesting results. But the problem is that they were often contingent on the multiplicity one conjecture. Okay, so it's a little bit like the Riemann hypothesis. I mean, it's not quite like the Riemann hypothesis, but it's like a bit. Okay, and so what I'm going to do is I'm just going to present these results, and then I'm going to shamelessly claim credit for each of them. Okay. So let me just set the stage here. So we suppose that we have a mean curvature flow that flows through singularities. So I'm going to use that regularity class that we've developed. And then it's going to be useful to talk about this time T-gen, which is the generic singular time. So that's just the supremum over all times, such that the mean curvature flow only has spherical or cylindrical singularities up until time T prime. Okay. So that's a time that we care about. That could be infinite. In this case, we only see these cylindrical or spherical singularities. I call them generic singularities for reasons you'll see in a moment. And so the first corollary is really a result due to Choi, Hasselhofer, Hershkowitz, and White in several combinations. And we just really removed the multiplicity one condition here. So it says that the flow restricted to the time interval up until the generic singular time is uniquely determined by the initial condition. So if you're flowing through these cylindrical and spherical singularities, there's only one way of resolving them, and that makes sense. Okay? And if T-gen is finite, then there has to be a non-spherical or non-cylindrical singularity at that time that's somehow responsible, that may be then responsible for non-uniqueness. Okay? Then the second corollary is based on the remark that I made before that the only genus zero shrinkers are cylinders and spheres. Okay? So if we put that together with our theory, then this says that if we start with a surface that has genus zero, so that's diffeomorphic to a sphere, then the flow will only incur spherical or cylindrical singularities, and it will be uniquely determined because we only see these spherical and cylindrical singularities. Okay? So now what happens if we don't start with a sphere? Well, then there is a result by Chodosh-Choi-Mantoulidis-Schulze, again contingent on the multiplicity one conjecture, which says that if we start with any surface that may somehow have these kind of non-cylindrical singularities, then we can slightly perturb the initial condition, and then these other singularities go away. So these non-cylindrical singularities, they were really due to a non-generic choice of the initial data. We can slightly perturb it, and then they somehow fall apart into cylindrical singularities. Okay, so the T-gen is then infinite. Does this make sense? Okay, so in the next 2 slides, I want to now talk about what happens if we don't have uniqueness and what we can still say in this case.
So I think I don't know if I asked you this before or not. For corollary 3, the perturbation, can you also get the same thing if instead of having a single guy, you have, let's say, a family of surface? can you perturb like the whole family?
No,
So that we just have generic singularities.
so you want to have a continuous family?
Suppose you have a one parameter family of.
I think that's not true. I think there's an example for a one parameter family.
Maybe my
Someone
student.
recently.
Adrian, my student, that's right.
Because you could try to then continuously deform these two different solutions. You could hope that the set of solutions allows a continuous path. So that would be an option. But yeah, I don't think you can perturb it completely.
That's right.
Yeah. Thanks for the question. Okay, so what I would like to do is now I want to consider the case where we start with a non-generic initial condition, and we may see non-uniqueness. And I want to kind of characterize this non-uniqueness and come up with some canonical flows that are canonical, but that show that they somehow explain why we have non-uniqueness. And so to do this, I need to briefly talk about this viscosity approach for mean curvature flow. Okay? And so this viscosity approach is based on this famous avoidance principle. So the avoidance principle says that if we take two smooth mean curvature flows, and if they're disjoint at some time, then they'll remain disjoint. Okay, so this is just a maximum principle. Look at the two nearby points, the most nearby points. The flow wants to curve, the surfaces need to curve away from one another, so the distance will keep increasing. Okay, so that's some other reason. And this idea is now used to give a viscosity theoretic formulation of this flow equation. And to do this, I'm going to pass to the space-time picture. So I'm not thinking of a mean curvature flow now as a family of hypersurfaces. Instead, I'm looking at their space-time track. So I'm thinking it of as a subset or post-subset in space-time. And then I can now define this weak formulation, which is called a weak set flow. So a weak set flow is now just a closed subset. It may not even be a space-time track of some smooth family of surfaces. It's just a closed subset of space-time that satisfies this avoidance principle for all other smooth mean curvature flows. Okay? So this definitely includes mean curvature flows, and it's somehow true for any initial condition, or it somehow even makes sense in a singular case. Okay? But there's a way you can cheat in this definition. So namely, if you're given an initial condition, you can just take the empty set later. Okay, so that definitely also satisfies avoidance trivially. Okay, and so now to get around this, people have been interested in looking at the maximal weak set flow starting from a given initial condition. And this is called the level set flow. And this has had a lot of other research around it because it has a lot of analytic significance. So people have looked at this a lot. Okay. So you can think about this. It's not hard. If you sit down for a few minutes, you can see that there has to be a maximal and a unique weak set flow, which is called this level set flow. And so this flow, so if we start now with some smooth initial data, then this level set flow agrees with the conventional mean curvature flow, with the conventional solution to the mean curvature flow, up until the time where the conventional mean curvature flow becomes singular and ceases to exist. So that is a good formulation, good weak formulation, but it's somehow true beyond the singularity of the conventional mean curvature flow. And at the singularity, we now may see some interesting behavior. But now it was shown by White that past the singularity, this flow, this level set flow, could behave in really weird ways. So it could exhibit this phenomenon called fattening, where the thing that we actually wanted to be a surface or look more closely like a surface may have non-empty interior. So it starts out being two-dimensional and then it becomes three-dimensional. And on the next slide, I want to convince you that I want to draw some pictures, show you how we should imagine this phenomenon, and I want to relate it to the phenomenon of non-uniqueness. Okay, so how do we do this? Well, I want to use, first of all, this idea from the previous slide to write down some canonical flows starting from a given initial condition. Okay, so I'm starting with a surface in R3, a smooth surface in R3, this one here, and I want to write down a few canonical flows that are at least uniquely determined. Okay, so the way I'm going to do this is I'm going to imagine that this surface bounds a compact subset K plus on the interior, so that red part, and then some other subset on the exterior, which is called K minus, the blue subset. Okay? And now I can come up with 5 different level set flows starting from this picture. Okay? So I can look at the level set flow starting from K plus and the level set flow starting from K minus. So they are uniquely determined. I can also take the intersection between both level set flows. That would then be the level set flow starting from the 2-dimensional surface M. And then I can also take the boundaries of the level set flow starting from K plus and the level set flow starting from K minus, because I like dealing with 2-dimensional things more. And these ones I will call the inner and outermost flow for reasons that will become clear in a second. Okay. So now if I look at this picture, and if I evolve all these sets by the level set flows and take the boundaries and so on, then for as long as the evolution of the mean curvature flow is smooth, this kind of picture will be preserved. Okay? So the evolution of K plus will just be that red subset. The evolution of K minus will be the blue subset. They will only intersect in that 2-dimensional surface M, and that's equal to M plus and M minus. Okay? So M is equal to M plus and M minus for as long as the flow is smooth. But at some point, I might hit some singularity. So, I'm drawing some kind of 1-dimensional schematic here, but you can actually imagine that this doesn't happen in dimension 1, but this is a good thing to look at. So now this red subset is the interior of this figure 8. The M plus and M minus is just the figure 8 itself, and K minus is the exterior of the figure 8. Okay? And so now, if you now evolve this shape by these corresponding flows, what you will see a second later is a picture like this. Okay? So now the evolution of the red subset is the union of the red subset and that purple subset. And the evolution of the blue subset is the union of the blue subset and the purple subset. And they intersect in that purple subset. So the purple subset is now the level set flow starting from M. So it will fatten. M, which was actually just 2-dimensional before, now becomes 3-dimensional, or in this picture, 2-dimensional. Okay? And now the outermost flow is the outer boundary of this purple subset, and the innermost flow is the innermost boundary of this purple subset. Okay? So the outermost flow basically tells you after you hit a singularity, that's somehow the furthest the flow could have progressed outwards after the resolution, and the innermost flow tells you the furthest it could have progressed inwards. Okay? And any other flow that somehow resolves a singularity of this type will stay between M plus and M minus. In that way, they characterize non-uniqueness. Okay, and so now we can characterize this picture using our resolution more precisely. So we can basically say what I just tried to suggest. So we showed that there is a time t fat called the fattening time, such that if you're prior to the fattening time, all these 3 flows are the same. So the level set flow is the same as the exterior flow, is the same as the innermost flow, the outermost and innermost flow. And then slightly after the fattening time, they're going to be different from one another, and M has non-empty interior. So this is exactly when fattening happens. And M is unique up until the fattening time, and therefore the fattening time has to be past the generic singular time. Okay? So this kind of confirms this conjectural picture. Any questions so far? Okay, so now one more corollary. So these innermost and outermost flows, they are now very canonical flows starting from an initial condition. And we can now give more structural results on these innermost and outermost flows. Okay? So we can now show that these inner and outermost flows are again almost regular. So they're smooth for almost every time t. The singular set is again 1-dimensional, which is what you would expect. And except at a finite number of points, all the tangent flows are spheres or cylinders. Okay? So the way you should imagine these inner and outermost flows is just like standard generic flows that somehow have these cylindrical and spherical singularities. And once in a while, they incur a singularity that causes non-uniqueness. But then the genus drops. And so that can only happen at finitely many points. Okay? So that's some of the picture. That somewhat confirms also what people have been expecting. Any questions? Okay, so now let me just give a little bit of an idea how the proof works of this multiplicity one conjecture. Okay, so here this again. And maybe the first thing I want to do is I want to kind of discuss two potential counterexamples that we should worry about when we want to prove this. So these are things that don't occur, but we worry that they might show up. Okay. So the first counterexample is where we start with a minimal surface. So I'm just drawing a catenoid as an example. Okay. So imagine that your initial condition is a catenoid. It's a minimal surface. So the mean curvature is 0. So this would just be constant under the mean curvature flow. So that would be boring. But now let me just add some noise. Okay, let me just wiggle this a little bit. Now I don't have a minimal surface. I just have something that's close to a minimal surface. And so now if I evolve this by the flow, it's going to move in time. There's going to be some dynamics. And, I could hope that this minimal surface is in some way stable. So I could hope that this kind of small noise will somehow die down while I will somehow decay while I evolve the flow, and it will somehow decay back to a minimal surface. But maybe while this noise decays, I'm not going to converge to this minimal surface, but to this minimal surface. Okay? Who is to say that I converge exactly to the same rescaling? Okay? So maybe I start with like a small perturbation of this, and then in 1 hour, I end up with a small perturbation of this. But again, it's only a small perturbation of this after 1 hour. So there's going to be still some movement. And now, since the surface has smaller scale, things are allowed to move faster, because at smaller scales, things move faster by the parabolic rescaling. So now maybe in half an hour, I see a perturbation of this minimal surface. And in a quarter of an hour, I see a perturbation of this minimal surface. And as the geometric sequence will converge. And then in finite time, I've converged to the blowdown of this catenoid, which is a multiplicity 2 plane. Okay, so this is potentially something that could occur. That we see this kind of small deviation, and you kind of converge in the direction of the kernel, in some kernel direction. Okay, so this is a behavior that we need to exclude. And so now here is a second, slightly more complicated counterexample, but this is the counterexample that we should actually look at. So, sometimes when you want to prove a theorem, you have to find the right counterexample that you want to, potential counterexample to exclude. And this is the one here. Okay. So here, sorry, I've been a bit too lazy to draw this in a 3-dimensional picture. So let me just draw a curve, and then you have to imagine that you kind of rotated it around an axis. So it's a rotationally symmetric surface. You just have to imagine it's, I'm just drawing the cross-section. And for a moment, maybe just ignore this part here. So what you see is 2 circles. So if you rotate them around an axis, you see 2 concentric spheres. Okay? So if you take a mean curvature flow starting from 2 concentric spheres, then their distance will continue to increase, will increase as I move forward in time. Okay? So that's not dangerous. Both spheres, they will collapse to a point, but the distance will increase. So therefore, the one sphere will collapse first, and then the outer sphere will collapse next. Okay. So in this case, I don't see higher multiplicity because I can talk about the distance between both spheres. But now let me change the situation and introduce this little thing here. So if you rotate this thing around an axis, then this looks almost like a catenoid, like a neck connecting these 2 spheres. And so now the way of arguing that I did before is not applicable anymore. I can't talk about the distance of both components anymore because there's only one component. Okay? So in some way, what you could imagine is that this catenoid is going to exert some force between these 2 layers, and it's going to kind of push them together. And as these 2 layers become closer and closer, this catenoid also becomes smaller and smaller, potentially. And this may allow the catenoid to kind of move around on the sphere faster and faster, and kind of everywhere try to kind of push these 2 layers together. This is kind of the thing that we're worried, that this is kind of, this exerts this force, and we can't really localize it in space and so on. And this is the behavior that I want to exclude. Okay, I'll get back to this picture in a moment. Any questions on this?
Is that it's meant to be a 2 plus delta?
2 plus delta. Oh, thanks. Yeah, never noticed this. Okay, so let me now tell you 3 ingredients that go into the proof, and let me show you how they're going to work out. Okay? First of all, let me remind you of this idea of the Gaussian area. So again, we're taking the ambient Gaussian, And so we assume that we have a singularity at time 0 and at the origin for simplicity. We look at this ambient Gaussian, we compute the Gaussian area. And as I told you, this is a monotone quantity. So if I take the derivative of this guy, then I get something that's non-negative. Okay? And the thing that I get in the end has to be a square of, like an integral of a square. And so this is really just the integral of this shrinker quantity. Okay, so this is non-negative, therefore I have monotonicity. And so this is, I think, what physicists call a global formula. Okay, so it's a formula relating two integrals with one another. But whenever there's a global formula, there's also a local formula. So a differential formula that holds at every point. And it has the property that if I integrate this formula, then I get back the original global formula. And this local formula takes this form. So it takes this ambient Gaussian, and then the differential operator is this conjugate heat operator. So it's something like a heat operator for the backwards heat equation on the mean curvature flow. And so if I apply this to the ambient Gaussian, then I just get this quantity here. So it's a simple computation, and it's essentially part of the proof of Huysgen's monotonicity formula. Okay, so this is the first ingredient. I want to kind of localize this a bit more. And now here's the second ingredient, which somehow strangely hasn't been known before. And this concerns what we call the separation function. So the separation function is a function characterizing the local separation of two sheets of a mean curvature flow. So here's just a one-dimensional picture, but this works in any dimension. So imagine that you have some time slice of a mean curvature flow that locally looks like these kind of two sheets. Okay, so these may not be two different components. They may, if I kind of follow in this direction, they may be connected with one another. Okay, but locally it looks like I have two sheets. And so now I'm defining just the distance of of a point on one sheet to the other sheet. So the way I can define this is to take the infimum over all radii, such that the intersection of my time slice with an R ball is not connected. Okay. It's just the distance to the nearby sheet. And I'm going to call a point x good if this circle here is transverse to the time slice. Okay? So this may not be a continuous quantity, but it's a continuous quantity near good points. There might be some weird jumps that happen when you're not at a good point. Okay? So it doesn't really make sense everywhere. Okay, so now here's the second ingredient, which weirdly hasn't been known before, is that at good points, so wherever kind of this has good regularity, the heat operator applied to log of the separation function is non-negative. Right? So this is a super solution to the heat equation. So in some sense, this says that up to like some diffusion, the two sheets want to keep separating, or they don't want to get closer together unless there's some diffusion, that they've already been closer together nearby. Okay. Any questions on this? Okay, so now let me put this together and show how we use this to show to exclude this second potential counterexample. So let me remind you again. We're going to start with this sphere, these two spheres that are connected by this little neck, this catenoidal neck, and I'm going to arrange things in such a way that I should see a singularity at time 0 and at the origin. And I worry that the singularity is modeled on a multiplicity 2 sphere, a double density sphere. Okay? And so now I want to get a contradiction to this. So I'm trying to just argue by contradiction. So first of all, let me define a function rcat, which is roughly the scale of the catenoid. You can define this in many different ways. Up to a factor, this should just be the size of this catenoidal neck. So this will go to 0 in time. And then I'm going to do something very naive. I'm just going to introduce a cutoff function. I'll call it eta. And I want eta to be equal to 1 near this catenoid in like an A times R cat ball. A is going to be some large constant that I'll choose later. And I want it to be 0 outside of a 2 times a ball of twice that size. And it should just satisfy the obvious gradient bound. Okay? So it's just how you would normally choose a cutoff function. Okay, so now I'm going to look at the average log separation. So I'm going to take log of the separation function, and then I'm going to integrate this against this ambient Gaussian weight. So if you now think about this using Green's identity, it's not too hard to see is that if you take the time derivative of this quantity, then this is equal to the heat operator applied to this guy, minus the heat operator applied to this guy, and then also the conjugate heat operator applied to this guy. So this would be a monotone quantity, but this thing is somehow not, or kind of this thing, the definition of this thing doesn't really make sense near the catenoid. Okay? So if this was a super solution to the heat equation everywhere, then this would just be a monotone quantity. However, this formula that I showed you on the previous slide is not true everywhere. So it's not true when eta is equal to 1. Okay? So now to get around this, I'm just going to replace this average log separation by some interpolation of log of the separation function in the kind of sheet-like part, and log of our cat, the scale of the catenoid, near the catenoid. Okay? So this is, I want to kind of regard this as some kind of substitute for the separation function. There should be a better function that somehow makes sense everywhere. I don't know what this function is, and I'm just going to take the scale of the catenoid. Okay? So this will maybe introduce as like a certain error, but it's a multiplicative error in here. So if I take the log of this, it will give me an additive error. So it's something that I can live with. And so now if I take the derivative of this guy, this average log separation with this modification, then I can use the two formulas from before, do a few integration by parts, and get a bound of this form. So this is bounded by something like 0.1 divided by tau. I need to make a large enough. Okay? And so now I can integrate this differential bound, and I get that this average log separation is bounded from below by 0.1 times log tau minus c. So tau goes to 0, so this becomes very negative. But remember, we want to get a uniform lower bound on the log separation. Okay? So potentially, this goes to minus infinity. But now remember, we've assumed by contradiction that we're converging to a double density sphere with this rescaling. So the separation function is roughly of the order of square root of tau. So if this is true, then this average log separation has to be smaller than 1/2 log tau, which is much more negative. And so therefore you get a contradiction for small enough tau. Okay. Let me take 2 minutes to talk about the general case, unless there are any questions.
So you mean you're getting implicitly a lower bound on how quickly they have to spread apart?
Yeah. So this one could, somehow this picture would fall apart too soon, that this is never going to be true for all taus. But if the picture were to persist, it would be too slow, which is not,
Okay.
So if the 1 over tau come from just from scaling,
Which one?
the 1 over tau, this bound.
Yeah, it's from scaling, yeah. It's yeah. Okay, so let me briefly talk about the general case. So in the general case, we have to deal with two different issues.
Maybe you could just go back for a second. As this thing's evolving, the geometry of the little catenoid piece is sort of changing in some possibly unpredictable way. So how are you controlling sort of the scale of our cat?
So in this particular example, so it doesn't really matter how big our cat is. The important thing is that it has to be comparable to the separation function in this transition region.
Okay, but what I mean is that your estimate at the end doesn't involve our cat.
Oh yeah, we also know that our cat, the time derivative of our cat, is bounded by epsilon times 1 over our cat, because we would know that if you see something that looks like a catenoid, then at a local scale, it will just very slowly move. Yeah. So that's something we do need. So we have to be a bit careful in choosing that. But it's that's a good question. Yeah. Okay, so what happens in the general case? So in the general case, you have to deal with two different issues. So you could see more than two sheets that come together. And you could also see cancellations of two sheets. So you maybe have 3 sheets, and suddenly the kind of 2 sheets cancel, and you just see a single sheet. And then somehow the whole thing could move back and become 3 sheets again, and you could see like weird behavior. And maybe even more importantly, you could see geometries in the flow that cannot be described by sheets or catenoids. Okay, so I showed you a simple example where we always assume that our manifold looks locally sheet-like or locally like a catenoid. but there could be many more complicated geometries. So for example, that would even be a simple example, would be that you see a catenoid, this kind of hole, and it could widen up and look completely different from a catenoid. It could look like a Grim Reaper cross R for a long time, and then the whole picture could come back and look like a bigger catenoid and then shrink again or something like this. Or you could see even more complicated geometries that we have never even classified, okay? And you need to say what you do with those. And so this is now another kind of interesting estimate that we use to kind of exclude or kind of say that these regions can be neglected. So what we do is the following. So first of all, we can define, this is done very often, the local scale. So a local scale at a point is the supremum over all radii, such that if I intersect my ball with a ball of radius r, restricted to a time slice or time interval size r squared, then within that ball and within that time interval, my flow looks very controlled. So in other words, if I renormalize the flow, like rescale the flow so that r log is equal to 1, then in a one ball, the flow looks very flat, like controlled injectivity radius, controlled second fundamental form and everything. Okay, so this is something like a bound on r log is better than a bound on the second fundamental form. So you can think of this as something like a maximal function in harmonic analysis. And so now what we do is we now look at the subset of points in our mean curvature flow. I'll call it M epsilon, where M looks locally at the scale, looks locally either like a minimal surface or like a plane or like many sheets, essentially. Okay? So this, in the previous potential counterexample, M epsilon was the entire flow. And therefore, we were able to do our conclusion. But M epsilon could not be the entire flow because there could be regions that look neither like this nor like that. Okay? But now, the ingredient is that I can now, is this estimate down here, which is that if I take essentially the integral of r log to the minus 2 over the set, the complement of the set, then I have a very good a priori bound of this. This is bounded in terms of kind of the distance of the two Gaussian areas. So this is a summable quantity. Okay? And this is kind of surprising because this exponent here is the critical exponent. And normally when you deal with maximal functions, then you would never have a strong LP bound for the critical exponent. You would only have a weak bound. But that somehow, the reason for this is because you may see bubbling in a way. But here we're essentially excluding these bubbles. They're minimal surfaces, and therefore we still get this kind of critical, this bound in the critical exponent. Okay? And so this basically tells us that we can completely ignore the complement of M epsilon. That one will not contribute very much to this average log separation. So the only important parts to look at is the almost sheet-like part and the part that looks like minimal surfaces, which is exactly what we had discussed in the previous counterexample. Okay, maybe I'll end here. Thank you very much.
Any questions?
Can you give me just an intuitive idea of why it makes sense to look at minimal surfaces as like potential counterexamples?
Yeah, well, I mean, I think the issue is that it's like in that first potential counterexample, that the minimal surface itself is not going to scale up or down. This is just going to stay constant. So but then if you look at a perturbation of the minimal surface, you won't be able to, then you have something that is almost constant. But being almost constant means that you could shrink or you could expand. Like if you have some surface where it's already going to shrink, or it's already going to expand, then if you perturb it slightly, it's going to still expand or shrink. But this is kind of does it make sense? Like
zero curvature is like the unstable point.
It's like it's the semi-stable one. And so if you slightly perturb it, it could become unstable or stable. Yeah.
Okay.
Yeah.
Another question?
Does everything still work from the ambient manifold is not R3, but just a general Riemannian?
Oh yeah, it still works.
Okay.
If you're still a Riemannian manifold, the only thing that doesn't work, but it's also not what we would promise, is that if the ambient manifold is not Euclidean space, then it makes sense to think about the limit as time goes to infinity, and in that case you may see higher multiplicity. But that's not what this theorem is about. Yeah.
Okay. If there are no further questions, let's thank the speaker again.